All right, let's talk about like some theoretical information about sound. So sound waves are longitudinal waves. So if you remember, like in the previous chapter, we talked about like the two different types of waves, transverse and longitudinal. So sound is a longitudinal or a horizontal wave. So a longitudinal wave, like you can take the wine glass example that I tried to give you. So when the wine glass, when you heat it, like it starts to vibrate, right? So when it's vibrating, what it does is like it's going to create one time the wine glass will move to the right, and then it's going to create a high density air, or a compression area, high density air kind of thing. And then at another moment, like when the glass moves away from the air, the air mass that's standing next to it, then there will be like pretty much a low density air. Okay. So this alternative high density, low density region that's traveling like in air, then that's what like creates the sound wave, or the sound that's coming from the glass. So this travels like the wave, as you can see here. The wave is traveling like this, and at the same time the medium, the air that's transporting the wave, they're also moving in the horizontal direction. So at one moment it was here, another moment it was here, another moment it was here, and so on and so forth. So you can see that like the elements or the one that are carrying the sound, they're traveling in the horizontal direction, and at the same time the wave is traveling in the same direction. Those kind of waves are known as horizontal or longitudinal waves. Okay. So this is just this low density area, sometimes known as rarefaction. Okay, rare. So you may call, like you may say, the air was rarefacted. Okay, so this succession of compression and rarefaction will travel in space and spread out, and then that normally creates the sound. Okay, so there are some categories of sound. Okay, so if you categories of sound, so sound can be categorized into audible sound waves. So the audible sound waves, they're mostly within the range of hearing of an average human ear. Okay. So, and the range is mostly in terms of frequency. Human ear, an average person, like 10 to 20,000 hertz. Okay, so this is our range of hearing in terms of frequency. We'll come and see it like in terms of intensity at the later point. Then others are known as infrasonic. Okay, infrasonic sound wave. So this frequency is like mostly tells you like how pitchy the sound is. Okay, so that is like if it is below our audible range. So a good example is like earthquake. Earthquakes are good examples of ultrasonic waves. Infrasonic. And then the other one is ultrasonic sound waves. That is more than the audible range, so it fits more than 20,000 hertz. Sometimes it's very pitchy, like for instance a dog whistle. It's it's outside of the range of our ear. So then, you know, there are some applications of those different waves, like for instance the ultrasonic wave. We use it for internal body imaging, right? So now speed of sound, you know, we know that like the speed of a wave, you know, just has a general way of finding it, lambda times frequency. Of course, if you know the wavelength and if you know the frequency, you can always use this equation. This is a general equation for calculation of the speed of a wave. But also, like the speed of sound when it travels in liquid and it travels in solid, when it travels in air, has different properties and different speed. Then as a result, like, you know, based on, you know, some properties of the given material, or based on the properties of the material, the speed of sound can be calculated as P over rho. This is like in a liquid. Okay. So in a liquid, like, you can find where B is Bulk's modulus of the liquid. It usually measures like the elasticity of the liquid, you know, how usually, or like how flowy the fluid is, how viscous it is. So that's a measure of where rho is an inertial property and its density. Okay, so using those two material properties, you can find the speed of sound in a liquid. Likewise, you can find the speed of sound in a solid. So V is equivalent to capital Y over rho. Again, rho is an elasticity property for solid. So this is in solid. Okay. So where Y is, we call it Young's modulus. It's a non-constant for most materials. Okay. Like B is also known for most liquids. And rho is, of course, it's the density. It's volumetric density. Unlike the linear density that we used to find the speed of wave in a string. Okay. So, but in general, like, you can find the speed of sound. The general equation is like, you know, what if like you have V equals some elasticity property, how elastic the material is, divided by inertial property. Okay. Okay, using those characteristics you may be able to find. Now, the speed of sound also depends on temperature. Okay. So the speed of sound in air it depends on the temperature. Mostly we use 340 meters per second, or, you know, as an average value for speed of sound in air. But, you know, of course, it depends at normal circumstances, at room temperature, usually at 20 degrees centigrade or something. But the general rule of speed of sound calculation is basically like, you know, 331 multiplied by the square root of T over 273K. Okay, so make sure that like your temperature is in Kelvin. Okay, then that gives you speed of sound in meters per second. Okay, so where T is the temperature in air. Okay, T is the temperature in air. So in addition to, you know, the speed of sound in air, probably other things that might be of our interest is intensity of sound. Okay, how, you know, whether sound is painful or not, instead of just talking about like the pitchiness, which measured by the frequency. What is the intensity of sound then? Intensity of sound. So the intensity of sound is basically like the average intensity of wave. It's the rate at which energy flows through unit area. Okay, so the rate at which energy flows per unit area. Okay, now it means like you have intensity and then energy flow over time, because the rate means over time, and of course, as we said, it's also like per unit area. So this is how you can calculate intensity. But you know that like energy over time, it's something related to the rate of energy is power, kind of. So you may substitute that like by the power of the sound that you have, and then divide that by area. So basically, like you can find the intensity of sound using this relationship. So based on the intensity, then you can categorize like sound waves in different ways. So intensities of sound, in terms of intensities, so sometimes there is a threshold of hearing. So if the amount of rate of energy crossing a certain cross-sectional area is small, really faint, then probably might not be able to hear that sound. So there is that, like we call that, like that's the threshold of hearing. So this is like faintest sound you can hear. So if it is below this, then most likely you will not be able to hear it. And in terms of intensity, this intensity is about 1 times 10 to the power of negative 12 watt per meter squared. That's what the threshold of hearing is. That's the first intensity category of sound. Second intensity category of sound is threshold of pain. Okay. So threshold of pain is the loudest sound that most people tolerate. Okay, so loudest sound that most people tolerate. Okay, so that's about like that intensity is about like 1 watt per meter squared. Okay, so anything between those two intensity levels, they're pretty much within our tolerance limit. Okay, so and then you may also find the intensity level. So the one we calculated was like the one that we just mentioned was like intensity, just simply intensity. But there is also another concept like that we use on a daily basis. We call it intensity level. Intensity is measured in terms of amount of power per unit area, but whereas the intensity level is like the sensation of loudness as a logarithmic function, as a relative logarithmic function. Okay, that's what the intensity level is. Okay, so intensity level is like it's a logarithmic function for our ear. So sensation of loudness to our ear is logarithmic. Okay, so as a result, like you can find the intensity level, usually represented by beta, as 10 logarithm of whatever intensity you may have divided by I naught, where this I naught represents threshold of hearing. This is what the threshold of hearing is. Threshold of hearing, which is 1 times 10 to the power of minus 12. Okay, so if you use this particular case, like for instance, like what if I want to find the intensity level of hearing, or the threshold of hearing in terms of intensity level? You can just simply substitute, like we know that the intensity level is like 1 times 10 to the power of minus 12 watt per meter square, divided by I naught. I naught is also the same, 1 times minus 12 watt per meter square. So this is going to give you beta is equal to 10 into logarithm of 1, but logarithm of 1 is 0, then as a result that will be 0. So our threshold of hearing in terms of intensity level is 0. Okay, you can also do like the threshold of pain, like for instance, for pain intensity level. Again, you'll be using, like, B for intensity of pain. Let's put it as pain. To look 10 into logarithm into I divided by I naught. That's the basic equation. And we already mentioned that, like, the intensity of pain is 1, so 1 divided by 1 times 10 to the power of minus 12. Okay, so this can be rewritten as like 10 times logarithm, so 10 to the power of minus 12, it's a numerator. I can take it as a denominator by making it positive, right? So it's going to be 10 into positive 12. The rest is 1. You can just leave it the way it is. Okay, then in logarithmic rule, I can take this 12 and bring it here and multiply that. So as a result, like 10 times 12 logarithm of 10. Okay, 10 times 12 is 120, and logarithmic log 1 is log 10 is just 1. Okay, so as a result, like our pain range, our pain is going to be 120. And you may say, like, what is the unit for this thing? And it's measured in decibels. Okay, those values are in decibel. So 120 decibel is like our threshold of pain. So the result, like, we hear between 0 and 120. It's just like for some jet airliners, or the threshold of hearing can be really more than 120. It can be 140, 150, and so on and so forth. Okay, so this is like in decibel. It's measured, intensity level is measured in decibels, whereas intensity is measured in watt per meter squared, right? So the last and most important item, I'm not sure if it is the last, but in sound, is like Doppler's effect. Okay, so what's Doppler's effect? Doppler's effect is like the amount of wave circles that you may cross if one of you are moving. What do we mean by that? Like, for instance, let's say this is sound source, and let's say you are the observer here. This is like, this is where the ear is, ear. So now what's going to happen is, like, when the sound, it's going to travel. So if the source is not moving, so you're generating like sound waves that are coming like this. Okay, so those waves are traveling like this, like the ripple effect that you see in the water. So those waves are going to come and cross your ears, basically. That's what's going to happen. Okay. So those and then those waves are coming, and if the source is not moving, then that means the frequency of so this wave will cross you one, and then after a certain time this will cross you so at equal intervals those things will be crossing your ear. So that means there is no any kind of amplification of the sound in terms of frequency. You just get whatever the frequency is coming from the source. Okay. But now the question is what if the source or the observer are moving? What's going to happen? Let's say the first one is let's say observer is moving towards the source. Okay. Observer towards source. So it means the source is not moving, so it's going to generate those waves normally, and then the sound has its own speed and so on and so forth. Okay. And those are equal intervals. It's not on this side and on that side either. Okay. Then now if you are the observer, if you are moving with a certain velocity, the velocity of observer, then when you are moving over here, you're going to cross those wavefronts at a rapid rate than if you are just simply standing and receiving that. Okay. So as a result, you will hear some kind of a pitched or a high frequency, or then you will hear an increased frequency. Okay. So likewise, if you are instead of moving towards the source, what if you are moving away from the source? Then that means when that happens, the amount of or the number of wavefronts that are coming from the source crossing your ear, right, is going to be somehow delayed, and then it's going to be lower in terms of frequency. Okay. So you'll hear a lower frequency. So in general, how much frequency will the observer hear? You can find that using this combination of the equation, so V plus V naught divided by. Okay. So what are those? So F is observer's frequency. That's what you are going to hear. Okay. This is source's frequency. And V naught is by how much the observer is moving or getting closer. So the observer speed, and it's positive if you are moving towards the source. It's negative if you are moving away from the source. It makes sense. Why? Because when you are moving away, then you will be hearing lower frequency than the regular or the real or the natural frequency of the sound. Okay. So keep in mind, make sure that when the observer is moving, make sure that in what direction is the observer moving. Is it towards the source or is it away from the source? And this V is the speed of sound in air. Okay. Depending on the temperature. Okay. So this is the first equation for Doppler's effect. Then the second one is what if now the source is moving, not the observer? Okay. What's going to happen? So let's say you're the source. Source is now here, but it's moving to this side. So what's going to happen is, like, since it's moving faster in this direction, what's going to happen is, like, let's say it's moving in this direction, the source. So now we're not going to get like a concentric kind of circles. Rather, the circle is going to be skewed like this. The wavefronts will be like much more closer on this side, but it's going to go further on that side. Yeah, this is presumably like, you know, circles, but I'm not drawing it nicely, but you'll get it. You see, if someone is standing here, if you're the observer here, this is source, and if you are standing here, the wavefronts that are coming on this side, okay, they're going to cross you like at a faster rate. It means like the number of cycles you complete, your ear completes per unit time, is going to be larger. Then as a result, like, you'll hear higher frequency. But if you're the observer on this side, see, the wavefronts that are coming towards you, they're coming relatively at a lower rate per unit time. So the number of those lines that are crossing your ear by standing here as a function of time will be smaller. That's what the whole idea of frequency means. So you'll hear lower frequency if you're on this side. It means when the source is moving away from you, then you'll be hearing lower. So what does the relationship say, like the way so in the previous example? So F naught will be just Fs. Well, F naught is like the observer here is going to be V divided by V minus Vs. Now we already defined V naught and Vs and V, but we defined F naught, Fs and V. Vs represents speed of sound, speed of source, and it's positive, then if it's coming towards you or towards, and it's negative if it's moving away, if the source is moving away. Okay, so you'll be using a plus in this example. We'll be using a plus for this observer, and you will be using a minus for this observer. Okay, so but what if both are moving? Of course you will combine the two equations that we just saw. Okay, so general cases, like maybe both moving. What if the source and the observer are moving? What are you going to do? So the amount of frequency the observer will receive is pretty much, it's a combination of what we had in the above two equations. It's going to be V plus V naught divided by V minus Vs. Okay, so we already defined F naught, we already defined Fs, we already defined V, which is the speed of sound in air. We already defined V naught or V0, which is the speed of the observer, and Vs is the speed of the source. So you will still be applying the same thing, like, V naught and Vs are positive, right, if sources moving of source or observer is moving toward. Okay, and V naught and Vs or Vs or V naught or and of course and or are negative if source or observer are moving away. Okay, so these are the two elements that I want you to know. But just to add a little bit here, have you ever asked it, like, what if the source travels faster than the sound speed? What's going to happen to the observer? What kind of sound will he be receiving? Like, let's say, the source is moving this direction, so you'll never, in this time, like, what you're going to have is, like, the circles or the sound waves, or they're being formed, is going to be like this. So here is the source, there is a small circle here, so a moment ago it was around here, so you see, and then a moment before that one you have here, so because the source was here, and then every time the source is moving, look, that's way, like, so this is the source, so the dots are the sources. So if it's moving faster than, like, before one wave reaches the other wave, then there is a new wave formed, and so on and so forth. Okay, so this is like the source speed. Okay, so let's say if you are an observer here, okay, what's going to happen? So you will see, mostly, like, commonly, like, you will see the aeroplane or an aeroplane, like, passing by, mostly jet fighters that travel, like, at speed, like at a Mach speed. Mach number, like, Mach number is usually presented as the speed of the sound divided by the speed of the source. Okay, so the speed of the source is, like, really faster. Then the first thing that you hear is not the sound. Like, if a fighter just passes by, the first thing that you will feel is not, like, the sound. The first thing that you will hear is, like, the shock wave. So there will be a shock wave formed, right? So you'll feel like windows and doors, like, tingling, and then after that, like, if a fighter just passes with its full speed, like, way faster than the speed of sound, say at 400-500 meters per second, then what you will hear is, like, the boom sound first. I mean, the shock wave first. The shock wave will start, and then after that, because the wave crests, like, that are crossing over here to each other, right? Those normally will create some kind of shock wave. Okay. So anyway, just for the sake of information, but with this we conclude the chapter. Then we're going to